Gauss-Markov theory in two parts. The first part will be the assumption of the classical regression model, and the second part will be the properties of the OLS estimates.
Hi, my name is Darshni. I'll be explaining about the first classical assumption, which is the regression model is linear in the coefficient and it has an additive error term which is correctly specified. Linear in the coefficient. This explains that the coefficient must be linear and it should not have any function with them such as beta square, beta cube and non-beta. Linear. Let me explain about the equation. Y represents the independent variable where beta 0 is the constant, beta 1 and beta 2, beta 3 are the coefficients, x1, x2 and x3 are the variables, and this is the error term. This is a typical linear equation. For an example, let's say y equals to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x square plus error term. This equation is linear by itself, but the variables are not linear. To justify an equation is linear, the coefficient must be linear. Second example, y equals to beta 0 plus exponential beta 1 x1 plus beta 2 x2 plus error term. This equation is not linear because the coefficient have a function which is exponential beta 1. The second element is the equation must have an additive error term. This is because to avoid the equation from being weak or incorrect with this graph. For an example, if you toss a coin and you won a head, but unfortunately you won't be getting a head in the first toss. So to avoid the repetition, you may add the error term to get the correct estimation. Lastly, the equation must be correctly specified. Here, the model must have the right variable to test its independent variable. The equation should not omit any variable that impact the equation or model. It also must have the correct functional form. For an example, if the equation has a cubic term as a function of variables in the curve, it must also have the value with the cubic term. Thanks. I'll pass to my friend to continue about the second assumption.
Greetings. My name is Adnan Anwar, your classmate for Econometrics 1, section BC100, group 2. This video is about me explaining the error term has zero population mean. I have roughly sketched the idea, drawn graphs so that you can better understand and grasp the concept. I hope you enjoy this video. Thank you for watching. Error term has a zero mean. This is one of the most important assumptions in econometrics. In a classical linear regression model, error term is assumed to have a zero mean. What does it mean? Let's take this model yi is equal to beta 1 plus beta 2 x2I plus mu I, where x's are not random. This we know from earlier assumptions. So what do? You pick up these x's. For each given level of x, you try to observe y's, and this is what you get. You get y corresponding to a given x which is distributed around its mean value. Please note that it's distributed normally. So all of these y values are distributed around the mean value. This line is actually passing through them. Well, now we have mean values of these deviations corresponding to a given x value this should be 0. If you see the red lines out there, the actual y values, as you have observed, these blue solid lines passing the mean values is actually a fitted line. So there might be certain values which are above this mean value, and there are certain values which are below this mean value, which are basically the errors. So on an average, this deviation should be 0. Supposedly peaks of these distributions would not be at the mean value, but here, the green line. Your fitted line will be like this, and that could be a problem because they will have a non-zero mean. They are not passing through the mean, and they will give you a biased estimate. These errors are not satisfying the main assumption that error has a 0 mean. Hence, it will not be kind of the estimate you generate out of the regression. Then they will not be unbiased. So this is one of the most important assumptions. Basically what I have said so far is that errors on an average should not be affecting the dependent variables. You may ask, why are errors generated then? It is because you may have omitted some of the important variables, or perhaps because you have not specified the model correctly, or maybe because of some miscalculation at your end. And that's why errors are generated. Thank you very much.
Hello, a very good day to you all. Today, my friend going to explain the assumption. Cheers.
Hi, I'm Ryan, and I major in financial engineering. Today I'm given a task to explain you about the assumptions, which was all explanatory variables are uncorrelated with the error term. Let's imagine there is some variable, which is y is the variable that you are interested in, which we also mean as dependent variable, while S1 and S2 will be the explanatory variable that you would like to include in your regression models, which we also call it as independent variable, while E is the error term. So the equation will be estimated to be in this form with the assumption of all explanatory variables are uncorrelated with error term. This means that there is unlikely the error term to be larger or smaller, or negative or positive when the explanatory variable is larger or smaller. This will also mean there is no discernible patterns in the graph and also very small correlation coefficient. However, these assumptions is violated most frequently when a researcher omits an independent variables is important from an equation. Let's say S1 is equal to A0 plus A1S2 plus A2S3 plus this is the error terms. Then we will sub these equations into these original equations, so that rewriting the equations, it will become y is equal to b naught plus b1 a naught plus bracket a1 plus b times s2 plus the error term and also these error terms. So to summarize these equations, there would be two constant terms, which was the b naught plus b1 a naught, this will be the constant, and this one, the error terms, will also be the constant. If S1 is included in the regressions, then it will be correlated with the error term, because S is the linear functions of part of the error term, which was this one, and the error term is correlated with one of the explanatory variable. So that the assumption, which is all explanatory variables are uncorrelated with the error terms, will be violated. So the OLS will not work. Thank you. That's all for my explanation.
Good evening, my name is Ahmed Izzuddin from Group B. Today I want to discuss assumption number 4, which is no serial correlation between error terms in OLS. Basically, this assumption is dealing with time series data and not cross-sectional data. The time series data is data provide the information or values of an event from time to time in some period. When dealing with time series data, often we assume that there's some correlation between past value to today value, or today value to future value. And when this happens, the values will form some sort of pattern or path or shape that seems organized. And this is not appropriate to the OLS, because OLS is a free estimation that the error terms cannot follow some set of pattern or shape or path. Let's say I have this equation when yi equals to beta 1 plus beta 2 x2I plus some error, when error is defined as this equation, when E is the error term of the equation and rho the autocorrelation coefficient, and U is classical error terms. What does it mean? It means the error today is depend on error yesterday by some amount of correlation and then modified by some elevation. When rho is positive, error will have some persistent, which means high error today will follow by high error tomorrow, and low error today will follow by low error tomorrow. Look at the picture. When we have low error today, our error tomorrow will be also low. It's not jump from high error today and low error tomorrow, or opposite of that. Also, when we have a high error today, our error tomorrow will be also high. When rho is negative, the error will have no persistent, which means high error today will be followed by low error tomorrow, and low error today will be followed by high error tomorrow. Let's look at the picture here. When we have high error today, our error tomorrow will be low, and the day after tomorrow our error will be back into the high value. Let me give you an example. Let's say we are estimating the weather temperature. When we have data of today, temperature is 0 Celsius degree, yesterday is 1, and 3 days before is 2 degree, and the winter is just started. The question is, what will you expect tomorrow's temperature? Is that 1 or 29? Most of us will say it will be -1, right? But the question is this assumption is appropriate? The answer is not. Why is not appropriate? Because rho is insignificant. There is no such real correlation between tomorrow's temperature and today's one. It maybe look like there are correlation between today's temperature and yesterday's. Then we just apply that correlation to estimate tomorrow's temperatures. or we just think it doesn't make sense that the temperature tomorrow will go up until 29, so we assume that temperatures tomorrow will just similar to today, but this assumption cannot be applied in the OLS. When this assumption is involved in OLS, the OLS is not anymore blue. This is what the assumption 4 tells us about. We cannot involve any error term serial correlation to make our OLS stays blue.
Hello, my name is Benjamin Kwan, and today we're going to talk about homoscedasticity. What is homoscedasticity? Homo means same, while scedasticity means variance, meaning that the error has a constant variance. First, I've prepared a sample data, as you can see on the left side of the screen, that looks like this. If I were to fit a straight line to this data so that I am using a linear model, for example like this, that best fits this data, the linear in my independent variable x, we can see that the errors which our model is making is constant across our independent variable x. They are the same, as you can see. As I increase my x variable, all the errors lie within the straight line error bar, like this. Next, we have the heteroscedasticity. There are some data points where x increase and there is a larger variance in y. If I were to fit a straight line best fits the data, for example like this, the errors are increasing in magnitude, as you can see at the side, as x increases. If I were to fit an error line, it doesn't represent a straight line. It is a slanted line to represent the error. It indicates that my errors are increasing along my x variable. So why do we care so much about our errors being homoscedastic? And if it's violated, it means our least squared estimator is no longer blue, meaning that it's no longer best, which means there are other estimators which are linear and unbiased. If I were to get heteroscedastic errors, there are some sort of information which is not included in my model. That's all for me. Thank you.
Hi guys, my name is Nur Izzat Haikal bin Lukman, and today I'm gonna teach you about the multicollinear.
Hi guys, my name is Haikal, and today I'm gonna teach you the sixth assumption, which is the no explanatory variable is perfect linear function of any explanatory variable. So there is two types of multicollinear. The first one is a perfect multicollinear. It means that, let's say, if I have a two variable, which is x1 is equal to x2. So, to make you understand more about this, I will draw you a graph of x1 and x2. As you can see from the graph, both points are touching with the graph. It means that variable x1 is and x2 is perfectly multicollinear together. So what happened when the graph look like this? It means that both x1 and x2 are non-perfectly exactly multicollinear, which is the second type of the multicollinear. Even though x1 and x2 are both correlated, it doesn't mean that x1 and x2 must be a perfect exactly multicollinear together. So to make you guys more understandable, suppose you decide to build a model of profit of tire. Assume annual sales tax paid by each store and annual sales of tire at each store as your independent variable. Since the tire store are all in the same city, they all pay the same percentage tax, so the sales tax paid will be constant percentage of their total sales. From this passage, we'll know that the X1 is equal to sales tax paid, annual tax paid, and X2, which is our second independent variable, is our annual sales of tire. If the sales tax is 7%,
Hello everyone, my name is Amir Hakim and my ID is 1102702265. Okay, so today I am going to explain about the assumption 7. The error term is normally distributed. Basically, assumption 7 implies that the error terms follows a bell shape. As you can see from the given graph, there are distribution A and distribution B. In distribution A, you can see that the mean is equal to 0 and the variance is equal to 1. In distribution B, we can see that the mean is 2, whereas the variance is equal to 0.5. Okay, as we can see from the graph, when the mean is different, the whole graph are shifted. As we can see from the distribution B, it is shifted to the right due to its mean is equal to 2. Not different from distribution A, where the mean is equal to 0. So it stays at the x-axis 0. Alright, so let me explain about the variance. So when the variance are different, it will show how different the size of the graph. As we can see in distribution B, the variance is 0.5, which is lower than distribution A. So the graph will look skinnier. Alright, so that is all from the graph. Now, let me continue. So, the assumption 7 states that the observation of the error terms are drawn from a distribution that is normal, as I just explained from the graph just now. Thus, it does not require ordinary least square estimation. So, it is majorly used on hypothesis testing, which uses estimated regression coefficient to investigate hypotheses about the economic behavior. Okay, so I guess that's all for me. Thank you.
Hi, ladies and gentlemen, my name is Quinfan, aka the assistant leader of the group. And I'm going to present you the properties of OLS estimate from chapter 4. And before I start my part, I would like to remind you that if all the 7 classical assumptions does not meet, the OLS estimator cannot be the best available. Let's recall back what are the 7 classical assumptions and that have already presented by my group mates before. Number 1, the regression model is linear, is correctly specified, and has an additive error term. Number 2, the error term has a 0 population mean. Number 3, all explanatory variables are uncorrelated with error term. Number 4, observation of the error term are uncorrelated with each other. Number 5, the error term has a constant variable. Number 6, No explanatory variable is a perfect linear function of any other explanatory variables. Number 7 and the last one. The error term is normally distributed. As this assumption must be satisfied, and if all has been satisfied, we can say that the OLS are blue. So what are blue? Blue is best, linear, and unbiased estimator. And for my part, I will be explain the first alphabet B, which is stand for best. I will graphically explain it to you. You can see that there's two axes here and two bell-shaped curves labeled as A and B. If you want to know which one is the best, we have to make comparison. That is why we have these two normally distributed estimate over here. And when we say it is best, it has the lowest variance. By looking at A and B, A is much more flatter than B and B is much more steeper than A. Both A and B have the same mean. They have the same average, but their variance are different. You can see the gap of the normally distributed of A is much more wider than B, and the B is much more closer to the mean. Therefore, we can say that B has the lower variance as compared to A. As a conclusion from here, B is the best as compared to the A. So that's all for the best, and my friend will continue to limit. Thank you.
Hi again. I will be presenting the property 2. Linearity of the coefficient. From the regression model equation, y hat equals to beta 0 hat plus beta 1 hat x1 plus e. This coefficient can be calculated as beta hat 1 equals to sum of xi minus xi mean times yi minus yi mean over the sum of xi minus mean of xi squared. This complicated formula can be rewritten as beta 1i equals to the sum of xi y times yi over the sum of xi squared. This is just the deviation from the mean form, where this one is xi minus x. Just that. And it can be simplified further by letting ki equals to xi over sum of xi squared. And substitute ki into this formula, you will get beta hat 1 equals to the sum of ki times yi. You can see that there is no square here or here, making this a linear formula. So as a conclusion of this formula, the estimator beta 1 hat is a linear function of the sample values yi, where the coefficient of
morning class, my name is Sean and today I'm here to talk to you about the properties of the OLS estimator. The property today I'm talking to you is the unbiased property. And what do we understand by being unbiased? By being unbiased, the best linear estimator of the true parameters is conditional to the sample values of the explanatory variable. If a parameter is unbiased, then the average value of the estimator will be equal to the true parameter, stated by this. And while when it's biased, the true value won't be equal to the true value of the parameter won't be equal to the explanatory variable. By proving, we can also prove that it's unbiased through this formula. When it's unbiased, the formula still stands that the expectation of B hat should be equal to P. So here we have the formula for B hat, and we substitute it into this Y formula. And what we get when we do that is we finally prove that the true parameter is equal to the explanatory variable.